Hello, this lecture will cover pages 164 through 170 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 8F, AC Nodal and Loop Analysis. We're going to continue on with phasor analysis techniques on AC circuits on page 164. Specifically, we're going to talk about nodal and loop analysis. Same thing that we did before, only we're working with phasors here again in complex math. If you take a look, we have a circuit here. And the circuit's comprised of a 24-volt source, sinusoidal peak volt source here at no phase angle with respect to a reference ground, and a 12-volt peak sinusoidal waveform here with a zero reference with respect to ground. So these two voltages here are in phase, and we want to determine the total average power absorbed and supplied by each element. And the way we're going to do that is we're going to do it through nodal analysis. Well, if you take a look, the same way we've done DC analysis, nodal analysis, by Kirchhoff's voltage law at node V1, and I'm going to refer to that as node V1 up here rather than just V. We talked about that. We have plus I1 plus I2 minus I3 equals 0. Well, what's I1? I1 is 24 at an angle 0, so I just wrote that as 24 minus the phasor V1 divided by 2. That's resistance. Plus I2. What's I2? It's 12 at an angle of 0, so we don't have to put that in. It's purely real. It's 12 minus V1 divided by J2. And then minus V3, which is equal to simply V1 minus 0 divided by 4 equals 0. Least common denominators are J4. I multiply through by J4. I clean up the expression using algebra very carefully. And I get V1, the phasor V1, is equal to 14.9 at an angle of 7.1 degrees. 7.1 degrees. Let me make sure of that there. I'm going to get a 63.43 minus the 56.3, and that should be equal to 14.9 at an angle of 7.13 degrees, and that's in volts. That's what that is right there. Knowing this voltage at that point here, here's the individual currents, so I can solve for current I1, current I2, and current I3. So now I know the currents gone through each of these elements. So if we turn the page, I'm going to give you an equation here that you're allowed to use on the exam. We'll prove it later on in the course, but the average power to an element is always equal to 1/2 the peak value of voltage times the peak value of current times the cosine of the phase angle. Don't forget, VV minus VI is the cosine of the impedance angle, or is the same phase as the impedance angle. Matter of fact, that is the impedance angle. VV minus VI is VZ. So if you know the impedance angle, you can just take the cosine of it. So I'm going to go through, and I know the currents, I know the voltages in the circuit through the previous analysis. The power in the 24-volt source, I'm just going to use this formula up here. And I end up with 55.4 watts, and that's supplied. Down here, the power in the 12-volt source, if you make a calculation on it, you get a negative value of power. That's absorbed. So that 12-volt source, if you look at the original circuit, is absorbing power, because the cosine of that angle, that negative angle, is a negative number. So I get a negative 5.5 watts absorbed. And the power here in the 2 ohm resistor and the power here in the 4 ohm resistor and the power in the J2 ohm inductor, I'm using this formula down here. There's two formulas for average power. Here's the first one. And by substituting in values here, you can see for voltage is Z times I. This voltage Vmax is Z times I max. Just make a substitution, you get this equation. You can use either one of these equations depending upon what variables you have. Notice I'm showing down here, here's VV minus VI, that's VZ. And here's VV minus VI, that's VZ. That's VZ in this expression. So for calculating the power in the 2 ohm resistor and the 4 ohm resistor and the J2 ohm inductor, I can make those calculations. Notice that the 2 ohm resistor, I end up with 22.09 watts. It's absorbed because it's a resistor. The power in the 4 ohm resistor turns out to be 27.83 watts. It's absorbed, it's a resistor. And the power in the reactive element is always going to be 0. I don't care if it's an inductor, I don't care if it's a capacitor. When you calculate power, the cosine will be 90 degrees or minus 90 degrees. And the cosine of 90 degrees or minus 90 degrees is 0. So 0 times anything is 0. So reactive elements do not absorb power. They borrow power during one cycle and they return it during the other cycle. Think about that. Ideal inductors and ideal capacitors don't use any energy over a complete cycle. They absorb it and they return it to the circuit. And that's why we're going to have to discuss something called power factor. Later on in the course, we'll discuss, during the last week, we'll discuss power factor. I mean, just think about it. People could start a business in their basement, put a lot of lathes in, and presses in, a machine shop. Very, very inductive loads, very high inductive loads. They're motors. They could use a lot of free electricity. Power company would never know. Because they're just borrowing electricity to get the inertia of those motors up. They're borrowing the power to get the inertia of those motors up, those big inductive motors. They're returning it during the next half cycle. Once the inertia gets gone. So what they have to do is they have to measure something called power factor. And then build them based on power factor. And the amount of real power they use. You might say, well, what about my house? I have a refrigerator, I have a washing machine, I have a dryer. There's a lot of there's a lot of motors in those. But compared to the overall resistive load of the house, those inductive loads are very, very small. So the electric company doesn't worry about that in a home. But in a commercial building where they have a lot of motors, high inductive loads, they charge people for that. And then you'll find out that if that power factor is significantly low, they'll make them compensate. They'll make them put capacitors in to offset that high inductive load. And they'll correct the power factor. It's called power factor correction techniques. What you're basically doing is putting in capacitance to offset the inductance to make that power factor go higher and higher and higher. But that's coming up toward the end of the course. But I went ahead and calculated the total power absorbed and the power supplied in the circuit, and then the conservation of power here says the power supplied equals the power absorbed, and you can go through and check, and it checks, and everything works out fine in that problem. Another example problem, we're going to use loop analysis on this to find I/O. Where's I/O? I/O is here. I/O is the current through that 2 ohm resistor right there. Might want to redraw that circuit. And we're just going to go around the loop. We're going to go around loop 1. That's a phasor current, I1, I2, and I3. 3 loops. -1. Then you stop and think, times I1. It's all phasor though. Then it's a negative J1. Then you stop and think. Times I1. Then it's a -2, and you stop and think. I1 minus I2, because I1 is the lead current, equals 0. You clean it up. Notice the coefficients now on the variables on these phasors are complex numbers. Same thing around loop 2, same thing around loop 3. And you get coefficients on I1, you get coefficients on I2, and you get coefficients on I3. Well, I didn't show I3 up here because there wasn't I3. You have to put it in as 0. Here's all three, I1, I2, and I3. Down here we don't have I1, so you'd have to represent that as a 0, I1. But you get your system of equations. Now, unless your calculator is an 89, a TI-89, some people can figure out how to do it on a TI-84, you can't solve matrices with complex numbers on normal calculators. I'm using what they call Cramer's rule right here, and I'm rewriting the coefficient matrix, and I'm calculating something called delta here by rewriting these first two columns and multiplying this times this times this, and then you subtract this times this times this. I don't know if you remember that from your math classes, but I calculate a delta for that coefficient matrix of 20.4 at an angle 11.3. Then I go ahead and I calculate I1 and I2, and I use the coefficient matrix, but for I1 I just substitute in the constants where the coefficients were. Here, 0, 12, and 0. Where am I getting that at? Getting it right here. Zero, 12, and 0. Then you divide by the coefficient determinant or matrix. And there's my answer for I1, 2.35 at an angle minus 11.3 amperes. I do the same thing to find I2, because all I want to find is I0 here, so I don't have to find I3. Just have to find I1, I2, take the difference. So here I do the same thing. I have the coefficient determinant, but make a substitution in for the I2 coefficients, put in the constants there. Instead of putting them in for the I1, like I did up here for the I1 coefficients, I put them in for the I2 coefficients here, 0, 12, 0. And I solve this by rewriting these first two columns out here and multiplying this times this minus this times this times this. Don't have time to go over that math technique. Or, again, if your calculator can solve complex numbers using matrix techniques or determinant techniques, that's the way to do it. Just plug all these in there and you get the answers. Here's I2. I0 is equal to I1 minus I2. I'll make the calculation. I get I0. Here's the answer for I2, and you could take that to the time domain if you wanted. I want to point something out here now. Let's do this same problem using nodal analysis. Let's do this same problem right here. And what we're going to do, let's see where it's at here. We're going to do the same problem, and we're going to use nodal analysis. Yeah, this problem right here on page number 166. Well, all I did was made a supernode right here. That's a supernode right there. And the variables I used was V1 here and V2 here. And I have a current there. I have a current here. I have a current here. And I had a current there. Forget it. These are the loop currents. I'm talking about branch currents now. I defined this current coming into this node cloud. I defined this current, and this current. You can find the currents if that voltage is V1 and this voltage here is V2. Notice the equation that relates the two. V1 is related to V2 through this 12 at an angle of 0 degrees. So you're going to see somewhere here I say that V1 plus 12 at an angle 0 is equal to V2. That's an important equation that I'm going to use when I do a substitution here. But notice that V1, if you have V1 and you add 12 at an angle 0, which is 12, you get V2. Your V1, you come up to this point, this is minus the plus, and you get V2. So that's how I get this equation here. So I'm just using nodal analysis. There it is. I didn't show the first line equation. Least common denominator here is a J2 times the quantity 1 minus J1. That's the least common denominator out of all of these. It's J2 times the quantity 1 minus J1. Multiply through by the least common denominator, and I clear the fraction, make my substitution that V2 is equal to V1 plus 12, or you can get two equations with the two unknowns, using this as one system equation here, using this as the other one once you clean it up and don't have to use substitution. It falls right apart when you get V1. Once you get V1, you can find I0. It's just V1 divided by 2. You get the same answer, minus a round off error. This is the same answer we got in the previous page. I think you would agree, unless your calculator can handle complex matrices, and you'd be back here on these equations. The easiest way to do this problem is nodal analysis. That's it. This is the analysis for nodal right here. And I got the same answer. So you can see nodal analysis a lot of time is the best way to go about it. Here's another problem here. An extra problem. I want you to notice here that I'm going to find V out. Here's V out. This is 12 at an angle 0. Here's Ix in this direction. This is 2Ix. This is a current controlled voltage source. 2 ohm resistor, a minus J2 ohm capacitor. Capacitor is always going to be negative J, you know that. Here's an inductor. It's J1. I just want you to do two loop equations. I1 here, I2 here. There's my one equation. I make a substitution here. I1 is equal to Ix. I1 here. This I1 is simply equal to Ix. Whoops. This I1 that we have defined here is the only current flowing through the 2 ohm resistor, so it's equal to Ix. And I go up here and put that in, and I get this first system equation. I end up with loop 2, go around loop 2, get that equation here. Same thing. Since I1 is equal to Ix, you can place it in here, and you get this. There's my two system equations. Now, I know I told you could have had three equations with three unknowns. You could have done this loop, kept Ix in the equation. You could have done this loop, keep Ix in the equation. You could have done this loop, keep Ix in the equation, and come up with a third equation for Ix. Well, there it is. I1 is equal to Ix. There's your three equations with three unknowns. You just have to put this in standard form with your three unknowns, I1, I2, and Ix. I think you can see this in standard form is a plus 1 Ix plus 0 I2. Let's start over again. Plus 1 I1 plus 0 I2 minus 1 Ix equals 0. That's that standard form. You have three equations with three unknowns. If your computer can handle complex numbers in matrices, you just work through that and end up with the answers. The answer here is V out turns out to be equal to 6.3 at an angle of minus 23.2 amps. Now, in this case right here, there's just two equations with two unknowns. Pretty easy to solve those equations. And I did it here using what we call Cramer's rule. There's my coefficient determinant, there's my value, and here's my value for I2. It's the coefficient determinant with the constants plugged in for the coefficients of I2. for the coefficients of I2, and I divide by the coefficient determinant. That's called Cramer's rule, and there's my answer in the frequency domain. Now, just for additional problems before you try the homework, I mean, I can show you some things here, but these are just problems you can look at. They give you answers. There's a problem right there. They want you to use nodal analysis to find V out. And there's the answer. Second problem, they want you to use nodal analysis again. Find I1 in the problem right there. You can see where I1 is. I1 is right here. And it's going from right to left. I1 is flowing in that direction. They want you to use nodal analysis on that. You have to treat this as one element here. You have to rewrite that as one element here. 3 plus J2. That's just 3 plus J2 for that impedance in that branch right there. When you write your nodal equation for that current. It's this voltage. Since the current's gone in this direction now, whatever you call this, let's call that point V1, and let's call this point V2. Well, if you take a look here, use the nodal analysis, this current gone from here to here is V1 minus 12 at an angle 0 divided by 3 plus J2. That's this current. Anyhow, you can work through that. Here's your answer for I1 in that problem. There's another problem right there they give you that says find Vx using nodal analysis and then check your answer with loop or mesh analysis. Same thing. They give you your answer right there. And finally, this would come in for the final lecture of this chapter. You can use loop analysis or mesh analysis, same thing, to solve for V out in that problem. And they also want you to use Thevenin's theorem to solve for V out in that problem. You should get the same answer, and that's the answer for that. So what we wanted to do in this lecture is basically show you how to use phasors in the frequency domain to analyze AC circuits using our nodal and loop techniques. The final lecture that I'm going to have now next is just going to cover AC Thevenin's theorem analysis with a maximum power transfer. Not too bad. It's just 4 pages I'm going to go over. Same techniques we used before. The only difference is the mathematics is using complex numbers. And it's really the only way to go if you're going to use a paper and pencil. Otherwise, you can use computer simulations and multi-sim to do this stuff as well. That would be the way to do it if you have to analyze a circuit and application. If you're working in industry. And that concludes this lecture.